Bismillahirrahmanirrahim. In continuation with the previous recording, we were talking about the divergence theorem. So this is actually the expression for the divergence theorem. Okay, so it means psi is equal to uh, closed surface of d dot ds. Closed surface of ds means we have to consider all the surfaces for the area, and this psi is also equal to uh, divergence of d, the volume divergence of d. Okay, so uh, let's have a discussion. We will solve a few examples on the divergence theorem, so it will be um, more clear to you people. Okay, so the first example is, this is actually the d in RCS. As you can see from the components, these are the RCS. Okay, and the x square plus y square is equal to 9. It means this is actually the r square. This is actually the circle equation. So x square plus y square is equal to r square. So in order to find the r, we will take the square root on both sides. Okay, x is equal to 0, y is equal to 0, and z is equal to 0, and z is equal to 2. Means x is fixed, that is 0, y is 2, y is 0, and z have the two limits, that is from z is equal to 0 and z is equal to 2. So okay, so uh, what are the different surfaces for this given shape? This is actually a cylinder, and this is one fourth part of the cylinder. Okay, or you can say it's a slice. Okay, one fourth slice of the whole cake. Okay, so this is one fourth part of the cylinder. So what would be the limit for one fourth? The z is given, that is from 0 to 2, and the rho is also given, that is okay, the r square is, or the rho square is 9, so the rho will be equal to 3 after applying the square root. Okay, and for the phi, as we have the one fourth, so the whole slice is actually 2 pi. So one fourth of the 2 pi is 2 pi over 4, we will get pi by 2. Okay, okay, so for this given structure, we have five different surfaces. Okay, so let's count these surfaces. The one is this one. Okay, and this actually uh, the right front. Okay, and it is in the direction of minus ax, because this is x, so minus x will be in that direction. Okay, now the left front is this one. Okay, and it is in the direction of minus ay, because this is y, so minus ay will be like that. Okay, this is the second surface. Okay, now the third surface is that top. Okay, the top, so it is in the direction of plus z, and the one is the bottom surface. The top and bottom are shaded. Okay, so it is quite clear. And the bottom is the fourth surface, and it is in the direction of minus a z. Okay, and the fifth one is this curvy surface. It is represented by these curved lines. Okay, and it is in the direction of arrow, because rho is in this direction, so this is in the direction of rho. Okay, so all these five are the surfaces, and we have to prove the divergence theorem. The question is, we have to prove the divergence theorem. So first we will find this side. Okay, because this is simple, and we will do it in a few minutes. Okay, and then we will switch to this side, and this is a bit lengthy because we have five surfaces, so we have to find all this formula for each surface, because for the surface 1, for the ds2, ds3, ds4. Okay, so this is a bit lengthy, so we will start from this side, and then later on we will solve this side. And if the equation, if the answer of these two is equal, so it means the divergence theorem would be okay, proven. So let's start from the solution. So first we will have find the dv. Okay, so dv is the volume integral for the, this is actually psi d dot d. Okay, uh, the the integral of d in rectangular coordinate system will be partial or partial. We have already discussed del dot any vector in the previous lectures. Okay, so from that lecture we have to write directly partial over partial x of dx plus partial of dy plus this. Okay, so after putting the values of dx which is given, this is actually the dx component in the direction of x, dy component and the dz component. So this is a dx, this is dy, and this is dz. Okay, so this. Okay, so we will after solving this we will get 6x plus 3 plus 3. Okay, so we will get 6x plus 6. Now the limits are given. These are the limits for this structure. So these limits are in cylindrical coordinate system because rho, phi, and z are the coordinates of cylinder. So, but here the given expression for the del dot d is in the rectangular coordinate system because of this x. So we have to replace this x into cylindrical coordinate system because we have no limits for the x. So how would we apply integration and will put these limits for the x? So there is no other way. So we have to uh, transform this x into cylindrical coordinate system by this formula: x is equal to rho cos phi. Y is rho sine phi, but there is no y, so later on we will have some y as well. So y would be equal to rho sine phi. We have already discussed these in the class. Okay, and z is equal to z. So by after transforming 6x 6 into x rho cos phi, okay, plus 6. Okay, so this is the whole expression. This is actually d uh, dv. Okay, uh, sorry, yes, the dv in the cylindrical coordinate system. So applying the integration and the limits, which is quite easy. Integration and then the upper limit minus lower limit, you will get 192.82. Okay, so now the method 2, psi is equal to, we have 5 different surfaces. So ds1, ds2, ds3, ds4, and ds5. Now I've already discussed that what are these surfaces. Okay, the front, right front, the left front, the top, the bottom, and the curvy surface. And these are the 5 surfaces. Okay, so the ds1 and ds2 are in the rectangular coordinate system because the left front and the right front surface have no curve involved. So that will be wholly solely in the form of xyz. So we will write the ds1 as in the direction of minus ax, so dy dz. Okay, and now ds2 is in the direction of minus y. Okay, from this. Okay, in the direction of minus x and the direction of minus y. So and ds2 is in the cylindrical coordinate system. This is like that. Okay, in the direction of plus az, that is top. In the direction of minus a, this is bottom. In the direction of rho, this is the curvy surface. Okay, so let's start from ds1, that is x is equal to 0 plane. So d dot ds, first we have to this is a similar method as we have done in the previous examples. Okay, so we have to apply the dot product, then we will followed by the integration. So d dot, this is d, given d in the rectangular coordinate system, and ds is also in the rectangular coordinate system, so there is no issue. But again, I'm telling you that we have to multiply only those coefficients in the dot product having the same unit vector, because after, if we if we multiply this ax component with ay and az, so by the dot product you will get 0. So don't waste your time by multiplying this with the different components. Okay, and this is the final solution for the dot product. And now the limits are given. For the y, this is 0 to 3, and for the z, this is 0 to 2. Okay, so uh, applying before the integration, we have to put x is equal to 0 in this expression. Why? Because this is in the x is equal to 0 plane. So x is 0 plane means we have to put x is equal to 0 in this expression. So as this is a single equation, and all are in the multiplying form, product form, so after replacing x is equal to 0, the whole term will be equal to 0. So that was all about the psi 1 for surface ds1. Now ds2. Okay, the ds2, this is ds2, uh, okay, dx dz ay, and this is minus, because this is in the direction of minus ay. So this whole expression is actually the dx which is given, this is the ds from here. Okay, so if again this is the ay, so we will multiply this component with this only, and this these two will be 0. This will be equal to 0, this will be equal to 0, so we will get this. And now we have to replace y is equal to 0, because this is in the y0 plane. Okay, given where is the equation, this one, y is equal to 0. Okay, and after that we will find for the z is equal to 0 and z is equal to plane as well. Okay, so now s is equal to 0, so replacing y is equal to 0 in this expression, we will left with minus z dx dz. So now applying the integration, because the dot product has been done, and the value from the dot product we get is minus z dx dz. So now d dot ds, this is d dot ds, applying the limits for dx and dz which is given. For the x, this is from 0 to 2, and for z 0 to for z for z it is from 0 to 2, and for x 0 to 3 given. Okay, so we will get psi 2 is equal to minus 6. Now for the surface 3, ds3, this is actually the this curvy surface, because it in the direction of a row. So actually this is d ds5. Okay, so uh, now this is in the surface is in the rectangular coordinate system, while the r is in the rectangular coordinate system. So cylindrical and rectangular coordinate system components cannot be dot producted. So for this purpose we have to transform the d component of from the RCS to the CCS, and we are only required the d phi component, because the ds is in the direction of a row. So we will only required, sorry, not d phi but d row. Okay, so only d row will be used, so we will transfer only the d row by this. And again x is equal to rho cos phi, replace in here. Okay, so we will get this, and also multiply with first row of this matrix, first row first column, so we will get this. Okay, now this is d row, so d row dot ds, this is ds, this is d row, and all the components are in rectangular coordinate system, so row will be equal to, again now our row is equal to 3, which is constant, so replacing the row values, uh, where we have the uh, the component, the term in the form of d, it means it is not constant, it is variable, and there are certain limits for these terms having d. Okay, but the term having non d, like rho or z in the this z. Okay, so we have to put the values for this. Okay, so now by replacing r is equal to 3, we will get this. And the dot product, the z limits are 0 to 2 and the phi limits are 0 to pi by 2. So applying the integration and putting the these limits, you will get 15.4. Okay, so now z is equal to 2 term, z is equal to 2 plane. So the z of rectangular coordinate system and cylindrical coordinate system both are the same. So there is no need to transform the RCS, the the dz portion of RCS into the CCS, because the dz portion of RCS is the same as the dz portion of the CCS. So this is dz portion. Okay, and this is ds. Okay, so multiplying these two, okay, now again we have x, because there is no limits for the x, so replace this x with a rho cos phi. By applying the dot product, we will get this expression. Okay, 0 to pi by 2 are the limit for the phi, and 0 to 3 are the limits for the z. So by applying the integration and putting the limits, upper limit minus lower limit, we will get this. Okay, and now consider z is equal to 0 plane. Okay, this was z is equal to 2 plane, and now z is equal to 0 plane. Okay, so uh, as we have the same expression in this, but just the difference is minus. Okay, because the z is 0 plane is in the direction of, because this is the z is 0 plane means this is the bottom surface, the base surface of the structure. So that surface is in the direction of minus z. So the only difference from this expression is this minus. And now we have to put as z is equal to 0, because this is z is equal to 0 plane, so this term will be equal to 0, and we will left with this only. Okay, again replacing x by rho cos phi, we will get this. So now the dot product is ready for the integration. So applying the limits of ds, the phi limits are 0 to pi by 2 and the z limits are from 0 to 3. So sorry, for the limits for the d row is from 0 to 3. So we will get this expression. So as all of the surfaces, the psi for all of the surfaces has been founded. So the last stage is we have to add up these five terms. Okay, psi 1 plus psi 2 plus psi 3 plus psi 4 plus psi 5. So we will get 0 minus 6 plus 33.41 plus 9 plus 156.4, we will get 192. Okay, and 192 from this as well here. This is the psi 192 for equation A, and this is the psi 192 for equation B. Okay, so uh, everything has been found, and hence the divergence theorem is proved. Okay, so that was all for the moment. Thank you.